let's try to derive the expressions, the analytic expressions for the energy eigenfunction. So the wave number, right, so the difference between the energy and the potential, we have the 2m, the difference between the potential and the energy, and for the harmonic oscillator is, if the frequency is omega naught, we have m omega naught x squared over 2 minus the value of the energy divided by h bar squared. This is this coefficient, and for large x, so let's explore this for large x, right, the potential dominates for some value of the energy. And so this looks like m omega naught, well, m squared omega naught squared x squared over h bar squared square root for large values of x, and this basically is proportional to x, right? There's some constant there. And so if we think of the exponential term, psi n of x goes like e to the minus alpha x, then it looks like we have something that ends up dying off faster for this case. And so there should be terms like that. And if we draw the ground state, we know that the ground state, let's say that the potential is shifted such that it goes to zero. The potential is something like m omega squared x minus x naught squared over 2. And so it looks like that. That's the potential. So, sorry, this is the potential. And let's say we want to draw the ground state. We already know that the ground state looks something like this. Okay, where the bending shifts. There. So that's the expression that we get. So we can sort of motivate that psi 0 of x is proportional to e to the minus some term x squared, and there's nothing else there. So this could be an x to the 0 kind of quantity. There's no further x dependence, right? That means there are no nodes, as we see there. But we can see a pattern emerge here. Right, so if I draw up psi 1, then that's x naught. I'm going to die off here, and I'm going to come through 0, and then die off like that. So I have one node, but I know that I have to have this behavior as x goes to infinity. So it looks like I have a term x1 e to the minus alpha x squared, where this thing gives me one node, and there it is, where it goes to 0. Actually, sorry, I need to shift this. So let's go back and thinking about this to, let's make this equal to 0. So this is x equals 0. And so the node is actually at x equals 0. This one does not have a node. So it looks like that. So in this case, x naught equals 0. Psi 2 of x is proportional to, now I need two nodes, right? So I'm going to come up and come down, come up and come down. So I have two nodes there. And so that function needs to be a quadratic, so it's an ax squared minus b kind of quantity, e to the minus alpha x squared. And so there are two nodes there. There they are. And so I can start to see the pattern here. And so if I do psi 3 of x, that would be proportional to, I'm going to multiply by x. I'll have a cx squared minus d kind of quantity. Right, this gives me one node. This gives me two nodes. And so I end up with a total of three nodes. I have the e to the minus alpha x squared term. And so I continue to increase the nodes. And let's try to go a little further. Psi 4, so psi 4 of x is now proportional to, I'll have an e x to the fourth minus f x squared plus g, right? This gives me 4 nodes, and then I have the e to the minus alpha x squared. Psi 5 of x is now this kind of thing times an x. So I have a hx to the fourth minus I x squared plus j e to the minus alpha x squared. So, right, this gives me this additional node. Right, makes them go through 0. This is the even number of nodes, and there we have a total number of nodes, which is odd. And so the parity continues to alternate, and we can see the pattern as we construct the higher energy eigenfunctions of the simple harmonic oscillator.